Okay, so we've graphed sine, cosine, and tangent. Now we're going to use those graphs. So this is the graph of sine x here. We're actually going to use those functions to graph their reciprocals. Basically, the only thing that I need to do to graph a reciprocal is I'm going to keep the x values and reciprocal the y values of the original function. So if I'm trying to graph cosecant, I will take the key points of sine, or the main points of sine. I'm going to keep the x coordinates exactly the same, and then I'll just reciprocal the y values. Okay, so keep x's and reciprocal, or maybe and use the reciprocal of the y's for our new points for our reciprocal functions. Okay, so I've pre-graphed the graph of sine here. We have the same scale that we were working with before. I'm going to zoom in on it a little bit. So this was where we were going up by pi over 6's. So we had like pi over 6, pi over 3, pi over 2, and so on. It's just not scaled like every single one, but same scale as we were working with before. Now the main key points of sine were the points where we have zeros, ones, and negative ones. So those are important points for our reciprocal. Okay, I also told you guys that the halves and negative halves were going to be important for the reciprocal. So first let's talk about the zeros, ones, and negative ones though. Okay, so for sine x, or y equals sine x, let's think about the point 0, 0. Start there. For cosecant, I'm going to keep the x, and I'm going to reciprocal the y. What's the reciprocal of 0?
0?
No.
Undefined.
Undefined. Can barely fit it here. Undefined. Sorry, I keep touching the... Just move it over a little bit.
But that was for tangent, not sine.
We're graphing cosecant. We're on the next lesson.
Yeah, I know. Oh.
So cosecant is the reciprocal of the sine function. Okay, so I have a vertical asymptote at x equals 0, right? That's going to occur at all the locations where I have y coordinates of 0. So where do those happen? Well, we just figured out that that happens at 0. Where else is y 0? Where else on this graph is y equal to 0? Sorry, can you help us with this? Where is y equal to 0 on this graph? Give me a point. Give me an x coordinate. I already got that one. Where else?
2 pi.
Pi, yes.
And the values.
2 pi. So all of these, when I reciprocal them, they will become undefined values. So the zeros, where the y is 0, those reciprocals will become undefined. So all of those points there, now the reciprocal graph has vertical asymptotes. They occur at x equals 0, x equals pi, x equals 2 pi, negative pi, negative 2 pi, 3 pi, 4 pi, 5 pi, and so on. Okay. What about the points where y is equal to 1? What's the reciprocal of 1? That's the negative reciprocal. The reciprocal of 1 is 1. So all the locations where I have y values equal to 1, those points actually stay the same because the reciprocal of 1 is equal to 1. What's the reciprocal of negative 1? Negative 1. So all the points where I have negative 1s, they also stay the same. Okay? So this point, pi over 2, 1, when I reciprocal that, it stays as pi over 2, 1. We said when we reciprocal pi, pi becomes an undefined, so this will be vertical asymptote where x equals pi. 3 pi over 2, negative 1. When I reciprocal that, it actually stays the same. The reciprocal of negative 1 is negative 1. And then 2 pi, where that was 0, that 0 becomes undefined as a vertical asymptote. So that's a vertical asymptote where x equals 2 pi. Okay, this isn't enough points, just like when we were graphing tan. This isn't enough points for us to be able to kind of figure out what that graph of the reciprocal looks like. That's why I need the halves and the negative halves. So if you notice here at 0.5, my graph has halves and negative halves, we said, at all these pi over 6 values. Here they are. I'm just literally looking on this graph. Once I have it graphed, I can just use the points. So we talked about how we can get these half and negative half points when we graphed sine before. But I'm just going to mark them all off all along my graph here. Here's all the halves and negative halves, right along this line and this line here, right? The halves and the negative halves. Okay, and we said those all occur for sine where we have reference angles of pi over 6s. What's the reciprocal of a half? What's the reciprocal of 1 over 2? 2. So these half points where I have pi over 6 half, the x will stay the same, but I'm going to reciprocal the y coordinate, which is 1 over 2. And I'm going to get 2 over 1, which is 2. So pi over 6, that point for our reciprocal function is going to be pi over 6, 2, instead of pi over 6 half, because the reciprocal of a half is 2. Okay? Same thing over here. I'm going to keep it in line. This one was 5 pi over 6. I'm going to keep it in line, but it's going to become the reciprocal, which is 2. Okay? What's the reciprocal of negative 1 over 2? Negative 2. So these negative halves down here, these points, again, keep them in line with their proper x coordinates. So they're still going to say at 7 pi over 6 and 11 pi over 6. But these points are going to become negative 2s. And now we're starting to get something where I think we can actually probably figure out what this graph looks like. Okay, same thing over here. This one will become positive 2. These guys are going to become negative 2 when I do the reciprocal of negative half. So they become negative 2. Note that I'm keeping them in line with their original x coordinates. The x's don't change, the y's do when I reciprocal. Okay, these two guys are going to become positive halves, or positive 2s, sorry. The positive halves become positive 2s.
So you just put 1 over negative 0.5? 1 over negative 2?
Yeah, or like when I think about 1 over 2, when I reciprocal that, I get 2 over 1, right? That's just 2. Okay, so here's my graph. I have to make sure that I don't cross over the asymptotes that have been developed here. Okay, this one's kind of just like the edge of one of them. And there's the graph of cosecant, the blue graph. Super helpful to graph sine first, and then you can just like follow along with where your x's are and reciprocal your y's. So the key values here are that the x's stay the same. And then I reciprocal the y's. So y reciprocals, oops, sorry. What happens when I do the reciprocal of 0?
It's undefined.
Undefined. So zeros become vertical asymptotes. Is everyone okay if I just put v dot a for that? What do the positive and negative 1s become?
They become themselves.
Yep. So they stay the same. And then how about the positive, negative halves?
We go 2.
Yeah. When we reciprocal those, we get positive and negative 2s. Okay? So if you can locate all those y coordinates, where are the zeros, those become vertical asymptotes. Where are the ones and negative ones? Those points stay the same because the reciprocal of 1 is 1, reciprocal of negative 1 is 1. And then if I can locate the half and negative half points, when I reciprocal those, I get half, or 2s and negative 2s. Okay, so that's kind of the idea. So domain here. What are you guys noticing about all the locations of the vertical asymptotes? Yeah, so it's essentially just like whole multiples of pi. Again, there's kind of like fancier ways to say this mathematically. But 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on, okay? So I think I can just say x is all real numbers where x cannot equal k multiples of pi, where k is an integer. Okay, and k can be 0, which is included in the set of integers. Sorry? Okay, so at multiples of pi, whole number multiples of pi and 0, that's where a graph is undefined for cosecant. Can somebody help us with our range for the blue function here? There's certain values that need to be excluded from our range. Jeremy? Okay, so how do we say that in a mathematical statement? Sorry? Yep. So rather than excluding that, that's like a range of values from -1 to 1. We usually say what y can equal. So y can equal 1 and above. How do I say that mathematically?
Y is greater than or equal to 1.
Y can be greater than or equal to 1, or it can be -1 and below. How do I say that?
Y is less than or equal to -1.
Good. Also, you could put -infinity to -1 square bracket in union with 1 to infinity with a square bracket on the 1. But since we kind of have to use this notation for domain of cosecant, we probably would stay in the same notation format here. Right. Yep. Liam?
On the test quiz, would you like use marks using 2 different notations for domain and range? So
Yeah, I would prefer you keep it in the same notation. Okay? Yeah. Yeah. Secant should be pretty quick right now because cosine and sine are such similar graphs, so we're just going to kind of do that process one more time, but using cosine as our main function. So I want you to mark off all the zeros, ones, -1s, and halves for cosine. So here's 1, 0, -1, 0, +1. Start with those guys. And then if you recall, all the halves and negative halves were happening at the pi/3s. You can even just look at your graph here. Once you have the cosine function graphed, here's half, -half, -half, +half, just marking off all those points there. Here's a +half.
Wait, so your first step is to mark all the halves?
And all the zeros and all the ones on the cosine function. Okay. So those are all the important points that we're going to use for our reciprocal function. Let's start with where the y's are 0. Zeros become vertical asymptotes. So I want you to locate all the x-intercepts here. All of those become vertical asymptotes at those values. So here, 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 and here. Those guys are going to become vertical asymptotes. So draw in your vertical asymptotes at those coordinates.
Wait, how do you know that that's going to be your vertical asymptote?
Because the y coordinate is 0, and when I do the reciprocal of 0, it's undefined. Okay, same as what we did for the sine function. So we've got our vertical asymptotes. You're going to label them. Okay, now I want you guys to locate all your 1s and -1s. We said those points actually stay the same because the reciprocal of 1 is 1 and the reciprocal of -1 is -1. So that's here, here, here. So 0, pi, 2 pi, negative pi, and negative 2 pi. Okay, and then we're going to locate all the halves. Those will become 2's. And locate all the negative halves. Those will become -2's. So I'm just going to make sure they stay in line with where they currently are. And we're just going to put those positive halves up at +2. So starting with these guys on the top. Okay, notice again that all my halves that have been reciprocal to 2 are still on the same x-coordinate. The x-coordinates don't change, just the y's. Okay, and then locate all your negative halves, and those are going to become -2's when I reciprocal them. Okay, it looks almost exactly the same as secant looks, except it's just shifted. It's a shifted version, because cosine looks the same as sine looks, but it's just a shifted version of it. Okay, so you get kind of these like mini parabolas in here. Oops. Okay. So that one's pretty straightforward. The domain of this just so happens to be actually the same as the domain of tangent. So you'll notice that the vertical asymptote locations here are actually the same as the vertical asymptote locations of tangent. So I'm actually just going to use that same domain that we used before. What you could use, another method, instead of saying like, okay, k is odd and k must be an integer, can't be 0, you could use like 2k plus 1 multiples of pi over 2. So that means 2k is positive, plus 1 is odd. So you can use that, or we can just use the same thing that we used before. So we'll specify that x cannot be equal to multiples of pi over 2, where k cannot be equal to 0, k is odd, and k is an integer. Okay, and the range actually just so happens to be the same as cosecant, so we're going to use the same range that we used above. So y must be greater than or equal to 1, or less than or equal to -1. Any questions for this one? It's pretty similar to the graph of sine when we do cosecant. Okay, for tangent, I already have tangent graphed on here for us. I'm just going to mark off those important points that we graphed earlier, which were the 1s, 0s, and -1s for tan. They are here. 1s, 0s, and -1s. Actually, maybe I'll do these ones in red. So this is just on the graph of tan itself. These were our important points that we graphed. The vertical asymptotes are also shown here in blue. Okay? Zeros. What did we say the reciprocal of 0 becomes?
Undefined.
Undefined. So look at all your x-intercepts here. All of those zeros become vertical asymptotes for our new function. So I'm going to pencil those in.
Undefined, so it becomes 0.
Yeah. So if zeros become undefined, then our vertical asymptotes, which are undefined, the reciprocal of that is actually going to become an x-intercept, which is 0. So my zeros of my tan function become the vertical asymptotes of my cotangent function, and the asymptotes of the tan function become the x-intercepts of the new tan function. So I'm going to mark off at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Those vertical asymptotes are undefined points. When I do the reciprocal of that, it actually becomes 0. And what did we say about 1s and negative 1s?
They say the same.
They stay the same. So I'm going to mark those off as if they're going to stay the same. So I'm going to mark them off in purple here so we can see a little bit better where our points are for our new function. And what we end up getting here is something quite similar to our graph of tan, but it kind of does the opposite. So it's like cubics that go the opposite way. Okay, I'm also just going to label my new asymptotes here. Fun graphs, right? I know you guys were all like laying awake for the last year wondering what the graphs of the reciprocal functions look like, so now you can rest easy. Oh, you looked it up on Desmos? Yeah. That's the smart way to do it instead of losing sleep, right? Okay, so can somebody help us with our domain for this function? I have vertical asymptotes at like negative 2 pi, pi, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on.
Would it be the exact same domain as the sine function?
Not as sine, but as its
Sorry, no,
reciprocal.
cosecant.
Yes, so it's going to be the same as cosecant. So I don't want multiples of pi where k is an integer. So no integer multiples of pi. So like 1 pi, 2 pi, 3 pi, 4 pi, and so on. What's the range of this function? What's the lower boundary to upper boundary?
It's just negative and it's infinity.
So it's everything, right? So we'll just say all real numbers for this. Same as tan, right? Just goes up forever and down forever. Make sense? So zeros become vertical asymptotes. Ones and negative ones, they'll stay the same. Halves and negative halves become 2 and positive, negative 2 and positive 2. Vertical asymptotes for the tan graph, they become zeros. Okay, so I'm actually just going to make an extra little note here. Vertical asymptotes of tan become the zeros of cotangent. Okay, so if zeros become vertical asymptotes, then when I do the reciprocal of a vertical asymptote, it must become a 0, right? That kind of makes sense.